So there we go. I'm hitting record. So yeah, the first question about this true false problem, it brings up a couple of regions, right? So one is the full circle and one is a half circle. And there are different versions, but I'm just going to do the top half here. And it said, here's R1 and here is R2. And we'll shade them in here. So it's supposed to be inside of this circle. I think it even specified a radius, maybe like radius 1 or something like that in both of these cases, just so you're really sure that there's no funny business going on as far as that's concerned. And then it says, if you were to do the double integral across R1 of some function, and of course, if you were actually doing the integral, it'd make a lot of sense for this to be in terms of r's and thetas. So r dr d theta there. If, you know, for setup though, I mean, you could just do x's and y's as well. And it's comparing with, if you were to integrate over R2, the same function, whatever it happens to be. And the hypothesis, or the thing that's asking about in this quiz question is this twice as much here? So if you take this half circle and you double it, right, will you get the full circle here, the R1 region? And the answer is false. And the reason why, I mean, so if you just had like area, for instance, if you knew about a very specific function, right? So if this was 1 in this case, right, then it would just be finding area in both of these, then that would happen to be true. But there are plenty of other functions where this would not be true. So for instance, if you were to integrate the function y, and of course we could put this into polar, it would just be r sine theta. So if you wanted the r's and the thetas, you could certainly get that over R1. And if you were to integrate y over R2, well, at least for R1, we're not going to find out the actual values for these things because that's, I mean, you can, but we can look at, for instance, R1. Can anyone tell me if we were to add up all of the y values for every single point in this region here? So every single point in this region, right? We're doing the double integral over a two-dimensional region here, and we're adding up all of the y values across this entire region. Can anyone tell me what would that double integral equal?
0.
It'd be 0, absolutely. And it's because, right, there's a lot of symmetry going on here. For every point up here with a specific y value, whatever it happens to be here, let's say a third, right? There's a corresponding point on the negative side where the y value is negative a third. And there's kind of this matching up, right? So if you were to add up all of the y values, or AKA we're doing the double integral of the function y over this region, that's going to give you 0. So this one right here would be 0. And again, we're trying to figure out if this is going to be twice what it is in R2. Now, of course, in R2, I don't...
Sorry to interrupt.
Yeah, go ahead. It's all right.
So when you're saying that, like, you're comparing the y values, is that like the y values for the volume? Because that's like what double integral is. Or is it like not that conceptual? Is it just comparing like y values and what cancels and doesn't cancel?
So I'm just doing the y values in the xy plane here. Sorry, I should have labeled my axes. So in the xy plane here, remember we're doing the double integral of y, right? So one way to think about this is that you're adding up across this two-dimensional region here, R1, and you're adding up all of the y components, right? So you don't really care about the x at all, but you just take y and you add all these things up. Another way that you could do this, if you wanted to think about it in the 3D sense, the 3D picture that would go along with this, is that this would be the plane z equals y, right? And so if you have the plane z equals y, here's x, y, z, and you have this plane, and I'm sorry, this is maybe a bad angle, so it's going to look a little bit weird, right? This plane goes something like this, and again, it kind of continues on. Oh, sorry, I have this backwards. It goes like this. So this is the YZ plane here, right? And so this would be Z equals Y. So it's a plane that continues on forever. And if you were to think about over this region that is the circle here, then you would have kind of half of your volume being above the XY plane. So something like this. And then the other half being below, the slice down the middle. And so all of your positive volume would cancel out with all of your negative volume, right? And again, really, because this double integrals are always net area or net volume in this case. And so if it's below the XY plane, it gets counted negatively. Just like when you're doing a single integral, if it's below the x-axis, it gets counted negatively. In comparison for R2, right? In R2, all of the y values for all of the points here in R2 are positive. And so you're summing up a bunch of positive things. And so, of course, when you sum up a bunch of positive things, this is going to be greater than 0. It doesn't have that symmetry that the other one does. And so there's not kind of all these negative y values. And so this will end up being greater than 0. And of course, if you take something and you double it, some number that's greater than 0 and you double it, there's no way that you're going to get 0 out of that. You can also just like choose very specific, other functions and whatnot to draw these things out. So maybe if I was to do this region here, and you just choose, something, a nice slanted plane on top, right? And if you go ahead and you cut it in half like this, here's maybe R2, and then thinking about R1 as the entire circle, right? If you were to take this volume right here and double it, right, you wouldn't get the overall volume, right? Because this ends up taking on larger values over here. So it really depends on the function that you have. A lot of words to say, it really depends on the function that you have. This would not be true for just an arbitrary function here.
That makes sense. Thank you.
Excellent. Okay. So if you would please, for future questions and whatnot, please put them in chat just so that we don't kind of lose any. And especially if I see that there are multiple people who are interested in the same question, then it'll be very easy to give that priority. I think that would be maybe a good way to go. So a couple from the practice exam here. Vote for, yeah, WebWork 26, number 4. I kind of was guessing that was coming. Let me check with the practice exam really quick here and see if there's randomization in it or not. Hopefully that these numbers all make sense, that there's not randomization in the practice exam. Otherwise, we'll need to specify more. All right, good. So these things don't appear to be randomized. So I can look off those. All right, so let me pull this back up here. What happens to do integration backwards? Okay, conceptual one. All right, so right now I don't see any overlap in questions. So I'm going to start off with practice exam number 6. Go from there. So practice exam number 6. Okay, yeah. So practice exam number 6 is this question right here. And hopefully you've gone and you've looked at the feedback. This is the double integral over some region R of e to the x plus y divided by x minus y dA, where R is the trapezoidal region with the vertices. Let's see, 1, 0, 2, 0, 0, negative 2, and 0, negative 1, or something like this. So this right here is our trapezoidal region, that is R. and asks to evaluate out this integral. You had a question in web work that was very similar to this. I think that the trapezoidal region was up like this, and it said to do the double integral, I think it was sine, but it could have been cosine of x plus y divided by x minus y dA. So this is a situation where you want to use your 1510 stuff, right? So this is the Jacobian and changing variables and all that. Integrating, these things where you have like a quotient of x's and y's is very difficult. And so you would like to do some sort of substitution here in order to make your integration a bit easier. And so as you probably remember from the web work homework, it suggests that you substitute maybe u to be equal to x plus y, and then v can be equal to x minus y. So very similar situation that we're doing for our problem. When we do that, the integral becomes e to the u divided by v. And then we need to switch out this dA, right? So this dA, this is kind of like in the xy plane here. And we would like to transform it right in terms of maybe u's and v's. And so the question is, well, what do we need here in order to switch something from x's and y's? Remember, this was something like dy dx here into something with u's and v's. And this essentially comes down to the Jacobian, right? The Jacobian of our transformation as you go from the UV plane into the XY plane. And so the big thing here you may remember from the Jacobian, right? It's going to be the determinant of some 2x2 matrix. And it's going to be something like the partial of x with respect to u, the partial of x with respect to v, the partial of y with respect to u, and the partial of y with respect to v. And the problem is, when you're actually going and you're choosing a transformation, quite often you set u equal to something and v equal to something because that's what's most useful in the problem. And yet when we go and we actually calculate out the Jacobian, notice that we need x to be our dependent thing, and it depends on u and v. So we need to solve like x equals in order to take those partial derivatives. And likewise, we need to solve y equals in order to take those partial derivatives. And so we need to spend a little bit of time here first taking this. Again, u was equal to x plus y, and v was equal to x minus y. Let me just check and be paranoid. And we need to solve these things for x and for y. And so, sorry, looking at chat here. Yes, I'm planning on posting this. So I'm recording these office hours and I'm planning on posting it at least on Piazza, probably on D2L as well, is my hope anyway. So yeah, now we need to solve these for x and for y. So let's maybe go ahead and add these together. This is a system of equations. There are lots of ways of solving system of equations. If you like the substitution method, use the substitution method, right? I'm going to be using the linear combinations method and adding one to the other, just because I noticed that when you do that, these y's are going to perfectly cancel out. And I'm going to get u plus v is equal to 2x. So that's why I decided to do that. So then I can get x is equal to 1/2 u plus v. So now I have x in terms of u's and v's. So if I wanted to right now, I could go ahead and start taking some partial derivatives, right? I could, maybe I'm going to rewrite this 1/2 u plus 1/2 v and just distribute that. But if I wanted to find the partial derivative of x with respect to u, well, take the derivative of this thing with respect to u and you get 1/2. If I wanted to find the partial derivative of x with respect to v, well, again, take the partial derivative of it with respect to v, you get 1/2, right? So I already know a few things here. I know that these are both 1/2s. We can also take this, now that we know what x is, we can plug this in here for x. And you can do it in either one, right? I just chose the first one, but you could also have plugged it in for the second one here. And that's going to help you solve for y, right? So, and you plug it into either one. I'm going to do the first equation, maybe as just like a test to make sure that I'm not lying to you, right? You plug it into the second one, and we'll all see that we get the same answer here. So this is going to be u is equal to half u plus half v, that's my x, plus y. And if I wanted to solve this for y, well, let's see, a full u, or 1u, minus a half of a u is going to be still half of a u. And then when I subtract away over the v stuff, I get negative half v, and this is equal to y. So we can just substitute that back in order to solve for y. Okay, again, partial derivatives of this are quite fast. If you want to know what the partial derivative of y is with respect to u, it's just going to be 1/2. And if you want to know the partial derivative of y with respect to v, it's just going to be equal to negative 1/2. So 1/2, negative 1/2. Now we can take the determinant of this. We're going to get negative 1/4 minus another 1/4. So again, we're just doing the good old determinant that we learned a long time ago, back in chapter 12, right? Where we just kind of do these diagonals, multiply them together, subtract away. And then we get negative 1/2. And then, yeah, there's a good point here that the Jacobian, right, when we actually figure out what should we put in front of this, how do we transform from x's and y's to u's and v's, you calculate your Jacobian, done, and then you need to make sure to take the absolute value of that. So this is going to be positive 1/2. Even though that we got an answer there that was negative 1/2, we want to make it the positive value, because this is essentially a stretching or shrinking factor here. Basically, we're saying that areas, as you transform from xy plane into the uv plane, get shrunk by a factor of 1/2. But it's still, right, area to area, you want everything to still remain positive, and so that's why you make it the positive here. We can see from this, right, that the antiderivatives of this are not going to be so bad. The last thing, though, is that we have to figure out, what does our region look like in the uv plane? And so in order to do this, probably it would take me another about 20 minutes or so. And so this is probably where I would vote to leave this problem. This is a problem in the textbook, as you probably saw in the feedback for this problem. So you can get the full work on how do you transform the region and everything. And it's very, very similar to what you did in the web work problem. But this is example number 3 out of 1510. And remember, in Piazza, there was a post of a PDF of the book. You can also get the book from the MSU libraries, just a digital loan for like 2 hours or something like this. So if you don't happen to already own the book, you can get the book and read the full solution to this, or again, just follow along basically what you did with your web work homework, and that will give you the result. Good. Any other questions about this problem here? All right, I've seen a few more votes for things, still not really any overlap. Let me do at least talk through, I know that people would like to hear about WebWork 26 number 4, at least on Piazza. I've seen a lot of requests for this. So let me pull up my WebWork really quick, and I'll say, maybe not do the full thing, but get to the part where everyone's getting stuck more or less. Talk about that, and then we can pull up some more from practice exams. So let's see, we have the cylinder R equals -8 cosine theta. Cuts from a sphere of radius 8. So sphere of radius 8. And we want to express the volume that the cylinder cuts out of the sphere of radius 8, centered at the origin, with a triple integral in cylindrical coordinates. And then we're going to go ahead and evaluate this. So that's the goal for this. All right. So maybe first of all, just let's review. We probably have done this, plenty in Math 133, and then also a little bit here in Math 234 as well, what this R equals 8 cosine theta looks like. And let's just first start off with it in the XY plane. So if you were to point in the direction of theta equals 0, that is, you're to point out theta equals 0 goes towards the positive x-axis, right? Plug in 0 where you see theta, you're going to get cosine of 0, which is 1. So you're going to get 8 times 1 is 8. So you're going to take 8 steps. 1, 2, 3, 4, 5, 6, 7, 8. And then you could plug in things like pi over 6 or pi over 4, pi over 3, pi over 2. Pi over 2 is maybe a nice one. When you do pi over 2, cosine of pi over 2 is 0. So you're going to get just 0. You can take 0 steps in that direction, the pi over 2 direction. Another nice one is maybe pi over 3. So if you do in the pi over 3 direction, cosine of pi over 3 is half. So you get 8 times a half, that's going to be 4. 1, 2, 3, 4. So something like this. Here it's a little bit more. Here it's still a little bit more. What this ends up being is a circle, top half. And then you can also do the bottom half down here. And you'll see you get the full circle. And it's a circle with a diameter of 8. Or another way to say this is a circle of radius 4. So this thing right here is a circle of radius 4. And that's kind of what this looks like. Now, if we were to take this and put this into XYZ space, well, and notice that it's missing anything about Z's, right? It has stuff about R's and thetas. There's nothing about Z's. Or likewise, if you were to put this in Cartesian with X's and Y's, again, you would see that there's nothing about Z's. And in the statement of the problem, it even alludes to the fact that this is a cylinder, right? So it's going to be a cylinder. Oops, I did a bad job writing Y there. Again, it's kind of sticking out in this positive X direction. This will maybe be 8. It looks something like this. And again, there are no Z's, so no matter what Z is, it doesn't influence this equation at all. So even if you're at Z equals 100 or Z equals whatever, you still get a picture of the same circle. And that's why, right, we call it a cylinder here. We can also draw in the sphere of radius 8. So the sphere of radius 8, well, okay, we already have going out to 8 in that direction. Go out to 8 in this direction. This would be -8 over here, and this would be maybe -8 down here. So a sphere, want to contain all these things, and then of course, go up and down. And so you can see actually that these things are going to intersect here because both of them go out 8 in the positive X direction. Now the cylinder does go on forever, but of course, right, eventually it exits this sphere. So when it exits the sphere, it kind of makes this interesting circly thing on top, maybe some weird stretched ellipse here. And similarly on bottom, get something like this. And so the question is, how much volume, right, gets cut out by this structure here, right? The cylinder here cuts out from the sphere a certain volume. And the question is, what is that volume? So like if you had some nice sphere here and you took a drill bit and you drilled through the sphere, what would, how much wood, I guess, would get drilled out here? So this is kind of what the structure actually looks like here. So if we were to set this up in cylindrical coordinates, a triple integral, anytime you're finding volume with a triple integral, it's always the triple integral of 1 dv. And then we're going to be using, it says, plus it's just in the cylindrical coordinate section, but it says to use cylindrical coordinates. So we transform the dv into r, dz, dr, d theta. And now we set up our bounds. So we imagine, right, if we're traveling in this z direction first, as is typical, right, how do we enter and exit this region? Well, as you go up, you seem to enter into this region through this red bit down here. This is where kind of the cylinder cut out from the sphere on the bottom. Right, so it's the surface there is a part of the sphere. It's part of the bottom part of the sphere there that would get cut out. And then when you leave, right, you leave through this green part on top. So somehow I need to give equations to what do I mean by this red part on bottom and what do I mean by this green part on top. And again, really, they're part of the sphere. And so the equation is going to have to come from the sphere's equation. And so let's go ahead and take x squared plus y squared plus z squared and set it equal to the radius squared, or 8 squared, which will be 64. Remember, this is a z integral, so we need its bounds to be solved z equals. So if I was to take this and rearrange, I could get z squared is equal to 64 minus x squared minus y squared. Thinking about this for a second, though, we want to be in cylindrical. So of course we can factor out a negative, and then x squared plus y squared is just going to be r squared. So that makes things a little bit cleaner there. You could have also swapped in at this point, right? X squared plus y squared equals r squared and gone from there. And then we need to take the square root if we want to solve z equals. And so when we take the square root, we get 64 minus r squared, and there's be a positive and a negative. And as you can probably guess, right, the bottom half of the sphere is going to correspond with negative the square root of 64 minus r squared. And the top half is going to correspond with the positive z values, positive square root of 64 minus r squared. Now, if you were to take this and smash it down into the xy plane, right? So take our structure and pretend, right, once you integrate with respect to z, there are no more z's. There's going to be r's and thetas, right? But those all perfectly live in the xy plane. So when you take this and you smash it down, it's going to live in this region right here, of course. That shading by gray didn't do a whole lot. But of course, we're going to be going over and looking at this picture anyway. You take it and you smash it down into the xy plane, and you're going to get that picture right there in the xy plane. And again, you play the same sort of game. You say, well, how do now I enter and exit this region? And remember, the next thing that we're going to be doing is using our r's, right? So we need to specify this in terms of r's. So when you take this and you point in lots of different directions, notice that when you enter into the region, you seem to enter in kind of immediately, right? So you enter in through the origin, r equals 0, right? So the origin has the equation r equals 0, so that's going to be this. And then you seem to exit through this circle thing. And remember, what we were trying to do back when we drew this circle thing is that we were trying to draw r equals 8 cosine theta. And so this right here is going to be the circle. R equals, great, it's already solved for r, that's wonderful, 8 cosine theta, 8 cosine theta. And then the last question that we have to ask ourselves is, well, when do we start and when do we stop for our angles theta? And notice that for this picture here, that you seem to hit this region everywhere between, and you'd have to really get a nice zoomed in picture, but everywhere between negative pi over 2 and positive pi over 2. You seem to actually intersect this region. Once you go beyond that, either over here or down here, right, you're no longer intersecting the region that you want to be integrating. And so you need to exclude those, right? So in this case, from negative pi over 2 to positive pi over 2. And now we've done all the work for the setup. We need to get a little bit into the actual evaluation for this in order to see where folks are making some mistakes. So let's go ahead and do a few of the integrations. When I integrate with respect to z, I'm going to skip a step here or so, right? When I integrate with respect to z, well, there are no z's there. It's just an r, so that's constant with respect to z. And then I would need to plug in my lower and upper bounds. So, right, my negative root 64 minus r squared and my positive root 64 minus r squared. This is the part where I said I'm going to skip a step here, and I'm just going to plug those right in. So I'm going to do positive root 64 minus r squared, and then I'm going to subtract away, and the bottom bound is also, it's negative, so minus a negative is plus square root of 64 minus r squared. Still have my r's and my thetas to go.
I had a quick question.
Yeah.
I'm sure you just said it, I'm sorry. So you are saying that theta goes from negative pi over 2 to pi over 2 because the circle touches the origin, so technically it like goes to the y-axis?
So that's kind of one way to think about it. But the way that I like to is like, right, theta is determining where you're pointing, right? If theta equals 0, you're pointing towards the positive x-axis. And then as you change your thetas, you're pointing in lots of different directions. But notice everywhere over here, when you're pointing in any of these directions, right? Theta equals 2 pi over 3, theta equals 3 pi over 4, theta equals pi. Notice that you never intersect with your region that you're trying to integrate over. The only times when you intersect with your region is when you are on the right half, and that's going to be from negative pi over 2 to pi over 2. Does that
Okay, that makes sense.
Okay, cool.
Thank you.
Mm-hmm. All right, so now we need to go ahead and integrate again. Of course, you have the same term being added to itself. So really you just have two of these things. So let me go ahead and just maybe write a 2 out here. All right, a 2 out here. And now this is going to be a little u substitution, right? So u is going to be equal to 64 minus r squared. And you're going to be integrating root u. So this is going to be, let's see, what, u to the 3/2. We're going to need a 2/3 here for when you take the derivative of that. Oh, and don't forget about the derivative of the inside. That's going to be negative 2r. Well, we already have an r here. That's good. But we don't have anything to cancel with that negative 2. So let's go ahead and put down a negative 1/2. So let's double check, right? If I take the derivative of this, do I get back to where I started? Well, again, the 3/2 would come down and cancel with the 2/3. That's excellent. We'd reduce our power by 1. So it goes from 3/2 down to 1/2. So that's where the square root comes from. We have the 64 minus r squared. And when you take the derivative of the inside, you would get negative 2r. So the negative 1/2 would cancel out with the negative 2. And we want the r to be there. So yeah, this is looking good. Let's go ahead and put in, instead of u, again, u is supposed to be equal to this 64 minus r squared. We can cancel a little bit here. And now we're going to need to be evaluating from 0 to 8 cosine theta. So let me go ahead. I'm going to take out, there's a negative sign here and a 3. So I'm going to go ahead and take all that really quick, a negative sign and the 3. So, okay, all my constants are now out. Now let's go ahead and plug in my 8 cosine theta. So we're going to have 64 minus 64 cosine squared theta, because it needs to be r squared raised to the 3/2 power. And then we subtract away, and when we plug in 0, well, we get 64 raised to the 3/2 power. There we go. And this is where folks are running into some trouble, because the natural thing to do here is, of course, to simplify this, right? And you can actually simplify it a fair amount. So one of the things, for instance, you may notice is that you can factor out that 64, right? And so you're going to have 64 raised to the 3/2 power, and then you're going to have this 1 minus cosine squared theta raised to the 3/2 power. And well, 64 raised to the 3/2 power, you can actually evaluate, right? The square root of 64 is going to be 8. And then what? 8 times 8 times 8. That's going to be, what, 512, I believe? I don't know. Someone can correct me on that. I think it's 512.
Yeah, that's right.
Super. That's not the kicker, right? That's not the important bit. The important bit is what happens with this 1 minus cosine squared theta. So of course you would want to turn this into sine squared theta, just using the good old sine squared theta plus cosine squared theta is equal to 1, right? And so that's going to make that a lot easier. And then you're going to be raising this to the 3/2 power. And so remember, the 3/2 power is just that you're going to take the square root of it, and then you're going to cube it. Well, when you take something, a square root of something squared, many times you just say that these cancel. So you take that, and then of course we have to cube it. And this right here is where the big error happens. Sadness. And the reason why that there's some error here is because there's certainly times where the square root of something squared, right? The square root of something squared does not equal just regular old whatever on the inside, that these things do not technically perfectly cancel. It works some of the time. So for instance, if you take like 5 and you square it and you square root it, well, then 5 squared would be 25, and the square root of 25 is going to be 5, right? And so yes, that works out. You just ended up with whatever you plugged in. However, if you were to do something like -5 squared and square rooted, well, when you take the -5 and you square it, you get 25. Sorry, I forgot my square root up here. Take the square root of that and you get 5. So your output in this case is not actually what you started with. The better way for this, right, the square root of something squared is actually another way to write the absolute value. So this, it'll be very, very close to whatever you input, but it will always be positive because you've squared it, and then you've taken the positive square root. So it forces it to always be positive. And like 90% of the time, it doesn't matter, right? When you look at these things and you, look closely at the problem, you see that, well, you're only going to be inputting positives anyway. This time, on the other hand, notice that what we're plugging in, the theta values range from -π/2 to π/2. So if I was to draw this on a mini unit circle over here, the theta values that we're plugging in are all over here. Now, from 0 to π/2 here, sine of theta is indeed positive. However, remember, because these are just the y values on the unit circle, down here, sine down here is actually negative. So by saying that these things are equal, well, you're right when it's already positive, but you've changed something when you're on this interval from -π/2 to 0. So you need to kind of break these things up. And so a better way to do this would be to break up from -π/2 to 0 and do the integral in this case, right? And then go from 0 to π/2. I also mentioned on Piazza that there's a faster way to do this, being a little bit clever here, because you may notice that when you cut this in half, right, if you were to only consider from 0 to π/2, only this top half, or better yet, on the full picture over here, it would be slicing this thing, let me use black, right down the middle like this, that there's symmetry about the x-axis. So if you combine the volume of this piece over here, ruining my picture, I'm going to hit back here, but if you can find the volume of that half there, then you can just double it, right? And that will give you the overall volume. And so the quick way to do this, noticing the symmetry here, is to just take this and only evaluate from 0 to π/2. And again, this is going to be what, 512. This is going to be sine cubed theta, because on this interval, it all works out well, minus 512 d theta. And then, of course, whatever that is, we're going to double it in order to get the full volume. I don't know. I'm not really happy with my 5 or my 2 here. 512. It almost looks like I was writing cis or something. I don't know. 512. So that's the big thing that I wanted to get to with this problem. Now that you have this, it's relatively straightforward and you'll get the right answer. Of course, you still need to spend a little bit of time. There's a U substitution that needs to be done in order to integrate sine cubed, but this is exactly like you did back in your Calc 2 days. Any questions on this problem here?
I have a quick question. So if this problem did not use cylindrical coordinates, would it be better, I guess, to use spherical coordinates?
I don't think so. Let me think about if there's The problem with spherical coordinates is that you would always enter in through the origin, and then you would exit out of 3 different surfaces depending on where you're pointing exactly. So there's sometimes that you would be exiting out of this green surface, which is part of the sphere. There's some times where you would be pointing, exiting out of this red surface down here, which is also part of the sphere. So those are kind of good. But then if you're pointing in other directions, you would actually exit out of the side here, the side of the cylinder. And so you would need to actually break this thing up, and you'd get these 3 different integrals. But here we were able to solve it with just 1 integral. And so that's why I think it would probably still be best to use cylindrical in this case.
Okay. And do you have any, oops, sorry.
Yeah, I was just saying it wouldn't be easy to determine exactly when you exit out of what surface. So breaking up the integral would be difficult.
Okay. And do you have any tips for like drawing like the intersections of these like different shapes? Because it's always a challenge for me to like visualize it properly.
Any tips for drawing? My favorite tip is to draw things in the RZ half plane. And then from there, you can spin this in order to give you the full 3D picture. It wouldn't work in this particular case right here, but let me give you maybe a quick example of a case where it would work. So let's say that I was tasked with maybe finding the volume or just kind of setting up an integral or something like this between, let's say, z equals the square root of x squared plus y squared. And so that it'll be below by this, and above by, we'll say x squared plus y squared plus z squared equals 1. Keep it easy. So if I wanted to set up what this kind of actually looks like, I really like drawing things in the RZ half plane. So here's R and here's Z. This works out well when you look at your equations in either cylindrical or spherical, and you notice that there doesn't happen to be any thetas. So if we were to go ahead and transform these things, this would say Z is equal to the square root of R squared. Remember, R is always positive, and so the square root of it squared is going to be, well, the absolute value of R, and again, always positive, so it's just R. So if I was to draw this here in the RZ half plane, it would look, and maybe I'll do green here. It looks something like this. It's just a straight line, right? The slope is 1. It's like the good old y equals mx plus b sort of deal. But here our independent variable, the thing that's going horizontally here, is R. And our dependent variable, the thing that's going vertically here, is Z, right? So you look at this and you kind of think it's like y equals x, but our variables are R's and Z's. So that's why it's a straight line of slope 1. So you get something like this. And now this one right here, if we were to go ahead and rearrange this, let me use purple, I suppose. We could do R squared plus Z squared is equal to 1. So right here, you could even stop, right? This is going to be a circle of radius 1. Again, our variables are R's and C's instead of X's and Y's, but circle of radius 1. And again, we're just going to restrict. I do an RZ half plane just because, again, R's are only positive. We don't really consider when you have negative R's. That's why I use the half plane rather than just the full plane here. And so if it's below by this, well, this will end up being a cone here. So if it's below by this equation here and above by the purple equation, well, then my region is going to be this right here. And so if you wanted to take this and draw a 3D picture of it, well, remember the things that's missing here is theta. So this is independent of theta. Theta can go in any direction that it wants. And remember, theta runs around the z-axis, right? If I was to draw my xyz plane here, x, y, z. Theta tells you, right, usually it starts at the positive x-axis and it runs around the z-axis, right? It tells you how far do you rotate around the z-axis. So if this doesn't have any thetas, well, theta can be anything it wants, right? So you could point out at theta equals 0 or point out at theta equals pi over 2 or whatever, right? And so basically what this is that you take it and you imagine it's attached to a pole and you hit the region and it spins, right? And it spins really fast. You get this almost ice cream cone shape. So again, kind of here's the surface, z equals r, or part of the cone down here. And here's the part of the sphere up here. And so this is a way to draw three-dimensional pictures in polar and in cylindrical and spherical that are independent of theta. So that's the hint, or that's the tip that I like for some of these.
Thank you.
Mm-hmm.
On the test, are we going to know, like, are we going to have to look at an integral and know, like, whether or not to do, like, spherical or cylindrical?
It's very possible. You know, I've seen plenty of exams where they don't specify what to do. They just say, here's an integral, go at it, sort of deal. And you have to decide whether you want to integrate it with, you know, in cylindrical or in spherical or just in Cartesian, stuff like that. Let me get caught up in chat here a little bit. There's some kind of small questions that I think should be fast to answer before we get into a full another problem here. So I see Kevin asks, why is sine squared theta plus cosine squared theta equal 1, but it's sine phi plus cosine phi equals 1. I've never heard of sine phi plus cosine phi equals 1. So it should still be squared. You'd still need them to be squared. Aiden asks, how can you tell when to have a function in the integral rather than just 1 times the Jacobian when using cylindrical or spherical? Well, it would have to specify a function to you, right? So if it wants you to calculate out a volume, then the volume is always 1 dV, right? But if it specifies, hey, calculate out the specific thing, so right, I've seen some exams, for instance, that say, or even just like the latest WebWork homework that says, do the triple integral of 5x squared plus 2 dV. And then it specifies some sphere or parts of spheres, right? So it needs to specify a function to you if it wants you to use a function rather than just this integration factor, the Jacobian thing, times 1. Okay, it looks like there's a few replies here as well. Cool. All right. So yeah, there's a few requests that I've seen in the chat about things that we discussed previously, and I am recording the office hours today, and I'll post this maybe on Piazza and in D2L. So I would recommend that if you joined late, certainly understandable, I'll post this and you can rewatch my explanation. And then if you still have questions, post them on Piazza. I'd be happy to help with those things. Okay, I know that there's certainly some that we missed. Practice exam number 2 and practice exam number 10 have gotten a couple votes here. So let's talk about those really quick. So practice exam number 2 next. Let E be the solid bounded by the lower half of the sphere and above by this cone. Express the triple integral below as an iterated integral in spherical coordinates. So x squared plus y squared plus z minus 1 squared is equal to 1. So this is below by this thing. So this thing should be on the bottom. And above by the cone, z is equal to the positive square root of x squared plus y squared. Express the triple integral below, and the triple integral is just the triple integral of e dv. Or if you'd like to, you can put 1 here. as an iterated integral in spherical coordinates, right? So, okay, so we're going to express it, and we could also even evaluate it. All right. Let's make sure here. Okay, so let's see, below by this sphere, and this sphere has been shifted up, it looks like, right? If we were to just kind of sketch what this thing looks like, debating here, this would also be maybe a fine time, since it's specified to us that we're going to set this up in spherical, right? Maybe let's try to use this RZ half plane idea. That'd be fun. So in this case, we have z is equal to, again, x squared plus y squared. That's going to be r squared. R squared. And the square root of r squared is just going to be r. So that at least gets it into cylindrical. If you would like to get this into spherical, which for the purposes of sketching it, maybe we can at least sketch it, because I think this is maybe just as good here to sketch it. Again, it's going to be the straight line sort of deal. It's going to have slope 1 and intercept 0. Looks something like this. Again, z is equal to r in the RZ half plane. We can also put this in terms of spherical, right? So in spherical, we have z is equal to rho cosine phi. And in spherical, r is equal to, put an extra equal sign there. R is equal to rho sine phi. And so long as you're not at rho is equal to 0, you can go ahead and cancel these things. And then you get sine phi is equal to cosine phi. Does anyone remember a place where sine is equal to cosine? What would the angle have to be that I plug in order to make sine equal to cosine?
Pi over 4, right?
Pi over 4, absolutely. And notice, remember what phi is. Phi is supposed to be the angle off the positive z-axis. Notice what angle that we've drawn here off of the positive z-axis. So off the positive z-axis, we need to go down pi over 4. So yes, these kind of, it's the same picture whether you were to draw it in spherical or in cylindrical, right? So this is going to be this cone thing. The other one requires a little bit more work. That's why I saved it for second. If I was to go ahead and take this and rewrite it a bit, let's do x squared plus y squared plus z squared minus 2z plus 1 is equal to 1. Getting ahead of myself there. So I've just expanded out this z minus 1 quantity squared. So a little bit slower, right? You'd have to do the full foiling. The first, the inners, the outers, the last. And when you do that foiling, this is what you get. We can go ahead and rearrange, right? So for instance, I see there's a 1 on both sides. That's why I accidentally wrote 0 over there. And we know that x squared plus y squared plus z squared. And again, there's a couple of different ways that we could do this, but I'm going to write this as rho squared here. And over here, if I was to move over the 2z, this would be 2, and z is rho cosine phi. Again, so long as phi is not equal to 0 and you're not stuck at the origin, then you can go ahead and cancel out a rho on both sides. And so we're going to have rho is equal to 2 cosine phi. This is going to be very, very similar to what we did when we sketched r equals 8 cosine theta, right? So up here, a little while ago, we sketched r is equal to 8 cosine theta, right? And we saw that it ended up being a circle with a diameter of 8. Very similarly here, but now we have phis and rhos. So let me go ahead and write down here, rho is equal to 2 cosine phi. Imagine if you were to plug in phi equals 0. So that is, remember, phi comes off the positive z-axis. So that is phi equals 0 is pointing straight up. If you plug in phi equals 0, you get rho equals 2, right? Rho is supposed to be this this three-dimensional radius from the origin. So you'd have to go out 2 steps. And as your phi increases, all the way maybe to, of course, phi equals pi over 2 would be pointing in this direction. If you plugged in phi equals pi over 2, cosine of pi over 2 is 0, you would end up intersecting the origin here. You're going to get a circle that has, again, a diameter of 2. Or another way to say that is a circle of radius 1. So this is the picture that we're getting here with this essentially circle that's been shifted up by a bit, and this cone, right, or the straight line here in the RZ half plane. And remember, we want the piece, it needed to be below by this, this equation and above by the cone. So if it's below by this, we're going to be at the, and above by the cone, above by the green line there, it's going to be this piece right here. And so if I take this and again, pin it to the z-axis and I spin it around, we're going to get a very interesting like bowl shape. So that's the thing right there that we want to find the volume of. So again, a triple integral 1 dv. If we switch this into spherical, we're going to have, again, the Jacobian here is going to be this rho squared sine phi. Don't forget that. D rho, d phi, d theta. Notice for all of this, there were no restrictions for theta. Theta never came up in any of these equations. That's why we were able to do it with the RZ half plane here. And so because there are no restrictions for theta, theta can run free, right? It can be anything that it wants to be. And you're going to generate the entire picture once you go around the positive z-axis once, right? So 0 to 2 pi here.
Where did you get the purple line that's like on the r-axis? Like what is phi equal to at that point?
So phi at that point would be equal to pi over 2. So remember, phi comes off of the positive z-axis. So when it's pointing straight up, right, that's when phi is equal to 0. It hasn't come off the z-axis at all. Here would be something like phi is equal to pi over 6. Of course, we already have drawn phi equals pi over 4. Here would be maybe like phi equals pi over 3.
How do you know to like stop there instead of continuing on?
So if you were to continue on any further after pi over 2, so for instance, if we went to phi equals 2 pi over 3, notice that when you plug this in here, you would get rho is equal to 2 times cosine of 2 pi over 3 would be negative a half. So this would end up giving you rho as a negative thing. But rho is always supposed to be positive, right? It's supposed to be this radius, this 3-dimensional radius. So that's one way algebraically that you could see this. You can also see that's just where it intersects the z-axis, right? So again, after that, it's going to be going over to the negative side. Our picture is not going to continue over there because again, it's an RZ half plane. Those are some kind of more the graphical and the algebraic ways that I would view this. From here, we need to think about how do we enter into our region and how do we exit our region. The first case is when we're going out in this rho direction, right? So if I'm in the RZ half plane, remember rho is going to be this radius from the origin. And we can see that, first of all, we only really intersect our region when we're pointing in these directions right here. So we're going to have to somehow embed that into our integral here shortly. But that's the only time that you actually intersect. So, right, for instance, I could go out in this direction here, and I would actually intersect my region. And down here, we would actually intersect the region. But it seems like we have to say, how do we enter into our region and how do we exit our region? Well, we seem to enter in immediately. As soon as we take the tiniest step off the origin, or rho equals 0, we enter into our region. And the way that we exit our region is through this purple curve, right? And this purple curve was this one right up here. Luckily, it's already solved, rho equals. So rho equals 2 cosine phi. And then we need to think about our phi values, right? What's the smallest and largest phi value where we're actually intersecting the region? Well, notice we didn't start until we hit phi equals pi over 4. That was that cone. And then we stop down here at phi equals pi over 2. 90 degrees off the positive z-axis. So pi over 4 to pi over 2. So this right here is the correct setup for this. From here, we can at least do two things relatively fast, and then that's probably where I'll leave it, and we have plenty of other questions to be talking about. Notice that in all of this here, there's no thetas. All of this is independent with respect to theta. It's all constant with respect to theta. And so once you have this all evaluated out, right, the last thing that you're going to be doing is evaluating out your theta integral, and it's not going to have, none of that has anything to do with theta. And so it's similar back in what, 15.2, a little bit in 15.3, right? We said if that's the case, then you can break up these integrals. Basically what I want to get down to is, and maybe you've just done enough Weber problems that you're happy with this, but I just want to plop down a 2 pi and say that that's going to be my theta integral right there. And really what this is doing is that we're separating it out, and all of this stuff here, the rho squared sine phi, d rho d phi, these bounds have phis in them, 0 to 2 cosine phi. So those ones you can't break up so easily since they depend on one another, but the thetas don't have anything to do with anything else. And so you can just plop down a 2 pi essentially. When you integrate with respect to rho, you're going to get rho cubed over 3, evaluated from 0 to 2 cosine of phi. Then you're still going to have your phi integral. The phi integral is going to take a little bit of work. 2 pi over 3. When I take rho and I cube it, well, of course, if I plug in 0, you don't get very much, 0. And if I plug in this 2 cosine phi, we're going to get 8 cosine cubed phi. And of course, we have that sine phi hanging out there. Still need to integrate this from pi over 4 to pi over 3, nope, pi over 2, d phi. We can take out that 8. We're going to have 16 pi over 3. And when you integrate this is just a relatively simple u substitution. U is equal to cosine of phi, and du will be equal to negative sine phi. And so this is going to be cosine to the 4th over 4. And can someone tell me I'm off by a little bit? Can anyone tell me what I'm off by? If you take the derivative, you don't exactly get back to where you started here. What am I off by?
It would have to be negative, right?
Negative, absolutely. Because when you take the derivative, the 4 would come down and cancel with the 4 on bottom. Good. I'd reduce my power by 1, so I'd go from cosine to the 4th to cosine cubed. Excellent, that's what I want. And then when you take the derivative of the inside, the derivative of cosine is negative sine, right? But I just have a regular old sine. So I need something to cancel out with that negative. And so the thing that cancels out with a negative is another negative. Okay, so there is that. Of course, the 4 and the 16 can cancel out a little bit. And when we go ahead and we plug in pi over 2 into cosine, you get 0. And then when you plug in pi over 4 into cosine, you get root 2 over 2. Remember, you have to raise this to the 4th power. I didn't really emphasize that with the 0 because 0 to the 4th power is, well, still 0. Minusing a negative gave me the plus there. And so when you take root 2 and you raise it to the 4th power, right, root 2 times root 2 times root 2 times root 2, you're going to get 2 times 2, which is 4. And in the denominator, you get 2 times 2 times 2 times 2, which is 16. So that's going to be 4/16, or that's going to be just 1/4. So we get 4 pi over 3 times 1/4. And so the final answer is pi over 3. All right, let me catch up on chat a little bit. Aiden asks, what's the main difference between a double and a triple integral? So I guess one simple way you could say it is how many variables there are, right? With a double integral, you're going to have 2 variables. With the triple integral, you're going to have 3 variables. Really intuitively, what they're doing is when you have a double integral, and maybe we could even start before that, when you have a single integral of f of x dx from some a to b, right? This has something to do with area, right? And when you have a double integral of maybe f of xy, and again, over some region now, and maybe it's rectangular, but maybe it's not, this has something to do with volume. Now, mathematicians are perfectly fine to say that this thing right here would have something to do with hypervolume, is the right thing to say. So it's a higher dimensional, right? So just like length would be a one-dimensional unit of measure, area would be a two-dimensional unit of measure, volume would be a three-dimensional unit of measure, and why not give reason to a fourth-dimensional unit of measure, hypervolume. And after that, we get lazy and everything's just hypervolume. So dimension 5 and 6 and all that sort of stuff. You just call them hypervolumes of different dimensions, sort of deal. But what I like to think of here is really, when I'm thinking of these things, I'm putting them in terms of the averages. That's where I get a lot of my intuition, especially because, right, hypervolume, what on earth is this thing? I like to think of these as, you know, when you're adding up this function, and maybe you could figure out what's like some average temperature in a room, right? So if this was a temperature function that depended on, right, in every point in the room, maybe it's only slightly different, but right, heat rises and stuff like this. So you would imagine that for a bigger Z value, maybe the room's hotter and stuff like this. Or maybe you have a heat source. Maybe you have like a lamp, or in my case, a computer, or lights and stuff like this that are giving off extra heat and all that sort of stuff. And then you could add up temperature for the entire room. And you say, well, what exactly does that mean? And I agree, that's a little bit complicated. But if you just say, what's the average temperature for the room, right? 1 divided by the volume of the three-dimensional region E, right? This would be average temperature. So in its purest sense, in its most mathematical sense, right, this is a hypervolume. But what it actually ends up getting used for in applications, right, is you're adding up some function in a three-dimensional region, right? So we have some three-dimensional region like the room or something like this that has X, Y's, and Z's coordinates, right? And you want to know maybe on average how hot it is in the room, or this could be anything. You could do all sorts of, you know, fun things at these points, how much pollen is there, and I don't know, whatever. So that's the main difference between double and triple integrals from an application standpoint.
Thank you.
Yep. Okay, I think the main thing after that is what practice exam number 10 is getting asked. Oh, wait. Oh, no, we didn't do that one. This one. So practice exam number 10, let D be the solid inside of the cylinder, below by the plane Z equals 0, and above by the paraboloid. So, okay, we have some cylinder here because it doesn't have a Z coordinate. And so inside of this, so let me just do a quick sketch here. This is a circle of radius 1, but it's not centered at the origin. It's been shifted up, right? And the center is 0, 1 here. So it's centered about this. So that's what it looks like in the XY plane. It's bounded below by Z equals 0 and above by the paraboloid. And we want to know something about the setting this up. So let me go ahead and draw the three-dimensional picture really quick. So in the XY plane, notice that this circle bulges out in the positive Y direction up to 2. So looks something like this. There we go. There we go. It's bounded below by z equals 0, and that's just the xy plane. So that's exactly this right here, z equals 0. And then it's bounded above by this, sorry, I never wrote down z equals x squared plus y squared. So it's above by z equals x squared plus y squared. Well, this is kind of the classic paraboloid, right? So it looks like parabolas opening in the z direction, whether you go in the x direction, so something like this, or whether you go in the y direction, something like this. And so you're going to end up, right, cutting out from this paraboloid, maybe some interesting circly shape here, maybe like a lima bean or something like this. And again, you want just the piece of the paraboloid that's hovering above this region here. And so here's your little cage. And the question is, I believe something about volume. Yes, so it wants to know what is the volume of this three-dimensional solid. So of course, anytime you have volume, this is always the triple integral of 1 dv. It mentions that we're going to be setting this up in cylindrical coordinates. So when you switch into cylindrical coordinates, you need r dz dr d theta. And I know this is a multiple choice question. And so, right, of course, we could rely on the answers and kind of doing a guess and check sort of deal. But let's just pretend for the time being that this, we didn't even look at the answers. And let's just kind of derive what the bounds for this integral would be. So if we're integrating first in the z direction, we have to imagine that we're traveling in this z direction. How do we enter into the solid and how do we exit the solid? Well, it seems like we enter in through the bottom, z equals 0. That's what it's bounded below by. And above by this paraboloid thing. And remember, the paraboloid has this equation z equals x squared plus y squared. Of course, if I wanted this in terms of r's and thetas, we know that x squared plus y squared is just equal to r squared. So I can put z is equal to r squared up here. Now, imagine that you've integrated with respect to z's, and the z's are gone, right? The graphical way that you interpret this is that you kind of take this solid and you smash it down into the xy plane. So there are no more z's left. So when you take this and you smash it down into the xy plane, you get this kind of original two-dimensional picture that I drew. So now we're here, right? And again, we're thinking in terms of r's and thetas. How do we enter this region and how do we exit this region? The next one up is maybe r. So as we have different points of view, right? As we choose different thetas, maybe starting off at theta equals 0, then maybe theta equals pi over 6, and maybe theta equals pi over 3 and pi over 2, and so on and so forth, right? You can see that you always seem to enter into this region as soon as you take the tiniest step off of the origin, off of r equals 0. As soon as you take the tiniest step off of r equals 0, you are in the region that you're integrating over. So how do you enter in? Well, it's through r equals 0. How do you exit out? Well, you seem to always exit out through this blue curve here. And remember the blue curve, I got this by drawing the circle of radius 1 that's been raised up a little bit. But of course, remember, we need it not in terms of x's or y's, but this is supposed to be an r integral. And so we need an r equals thing. So I need to take this and I need to turn it into an r equals thing. So, okay, this takes just 30 seconds or so. X squared plus y squared minus 2y plus 1 equals 1. So that is, I FOILed this out. X squared plus y squared is r squared. So looking at this bit, the 1s can cancel. And if I move that 2y to the other side, I'm going to get 2r sine theta. Now, assuming that we're not stuck at the origin, which is, right, we already took that into consideration. We're going to go ahead and cancel out those r's, right? We're not dividing by exclusively 0 here. And we get r is equal to 2 sine theta. We've graphed these a few times throughout the office hours today, right? We know that this is going to be a circle with diameter 2, and just the sign says that's going to be bumping into the y direction. The cosine, it was in the x direction. But yeah, so a circle of diameter 2, or you could say radius 1. So maybe that's not super surprising. So here we're going to have 2 sine theta. That's how we're exiting through. And then finally, we have to think about when do we actually hit this region that we're integrating over, what theta values. Well, maybe at theta equals 0, you just barely skim it. Can't quite tell. Certainly at theta equals pi over 6 and all these, 2 pi over 3, we're all hitting the region. And then maybe at pi, again, you just barely skim it or so. But then after that, as you point kind of down here in quadrants 3 and 4, you never seem to hit the region of integration. And so when do you start and when do you stop? When do you actually hit the region? That's going to be from 0 to pi. And that right there is the correct setup. And so, of course, for this problem, it just said to set it up, and all of the multiple choice things were setups like this. You didn't have to go on and evaluate. I don't know what so yeah, A is equal to 2 sine theta, B is equal to r squared. So for me, that's option 3, but I think the orders are randomized. All right, let's see. I don't think there's been any things in chat, so I'm all caught up there. I've seen a few things from homework 27. That might be a good one. The earliest homework 27, it doesn't seem like there's any overlap, but homework 27 number 5 was the first one that was asked. Then homework 27 number 4, homework 27 number 2, homework 27 number 7. Yeah, they're all different. So okay, we'll do homework 27 number 5. That was the first one asked. Homework 27 number 5. So homework 27 number 5 says express the volume of the sphere. Mine is x squared plus y squared plus z squared is less than or equal to 49 that lies between the cones. Lies between cones. Z equals the square root of x squared plus y squared, and z is equal to the square root of x squared plus y squared divided by 3. And then maybe we'll do the express, but we won't do the evaluate. So, all right, there's a couple different ways, but let's go ahead and maybe visualize this first, right? So if I wanted to visualize what this actually looks like, when I go ahead and start transforming this, so for instance, I know that this is going to be r squared, and let's just look at the outer region of this. Let me write this down here. So x squared plus y squared is going to be r squared plus z squared is equal to 49. It's just the outermost bit. Of course, we're going to be doing the entire solid, so it's going to be inside of this. And then for these cones, the first one is going to be z is equal to the square root of r squared, or just r. We've done this a couple of times. And then the other one here is going to be z is equal to the square root of r squared divided by 3, or that's just going to be r divided by root 3. So it's going to be, again, a straight line sort of deal when we draw this in the RZ half plane, but it's not going to be as steep of a slope. So again, here z is equal to r. I'll draw in green. This is going to be just a nice straight line with slope 1, intercept 0. Z is equal to r divided by root 3. Again, it's going to be a straight line with intercept 0, but here the slope isn't as big, right? Because we've divided by some number, divided by root 3. And then finally, r squared plus z squared equals 49. This is going to be a circle, or really, I guess, a half circle, since we're just in a half plane, of radius 7. So we get something like this. And so we know that it's supposed to be inside of the circle and trapped between these cones. So it's going to be this bit right here. And of course, if I wanted to take this and draw a 3-dimensional picture of it, I could take this and spin it around the z-axis. Notice that none of these had anything to do with theta. So theta runs free. this here, this here. And so, I don't know, it's almost like a hollowed out top or something like this, right? Some very interesting bowl, or it'd be standing at just a point. All right, so this is the thing that we would like to find the volume of, right? So express the volume inside the sphere that lies between the cones. So we're trying to find volume. Anytime you're trying to find volume, you're integrating 1 dV. In this case, well, it tells us to use spherical, but also we're inside of a sphere. So even if it didn't say use spherical, the fact that it's inside of a sphere is awfully, pushy towards spherical. So we're going to do the whole rho squared sine phi sort of business, d rho, d phi, d theta. Again, our thetas, right, none of our equations had anything to do with theta. Theta didn't show up once. And so theta can be anything it wants to be. We don't have any restrictions on theta. And when that's the case, right, it goes from theta equals 0 to theta equals 2 pi. When you look at this three-dimensional picture, right, and again, we're going to be now thinking about how do we integrate with respect to rho. Remember, rho starts off at the origin, and it's kind of a three-dimensional radius, right? It kind of emanates out of the origin there. And so if I was to go out of the origin here, the way that we're going to enter into our region of integration seems to be, again, right after we leave the origin. Right after we leave this, we're already inside. And so the bottom bit is going to be rho is equal to 0. The way that we leave always seems to be through this bit right here. This is part of the sphere, right? So however we intersect that sphere, that seems to be how we're leaving. And so, well, this came from when we were drawing it before, we did r squared plus z squared is equal to 49. Of course, since we actually want to integrate in spherical, we could write this as rho squared is equal to 49, or that's just going to be rho is equal to 7. So r squared plus z squared is, of course, equal to rho squared. You can just go through the equations and find it that way. Or we could start over from the Cartesian, right? Maybe that's a little bit easier to say, x squared plus y squared plus z squared, that's rho squared. When does that equal 49? Well, exactly when rho is equal to 7. Okay, so from rho equals 0 to rho equals 7. And then phi, right? When do we actually hit this region? So for instance, when phi is equal to 0, when you're like basically along this positive z-axis, notice that you don't hit the region at all. Even when you go down farther, right, you don't hit. It's only when you line up with this green curve right here, this green straight line, that's when you enter in. And you exit through this purple, right? And after you go beyond that purple, again, you don't hit that region that you're integrating over at all. And so we need to take those green and those purple curves and put them into spherical. So for instance, let's go back to the green one really quick. We've already done this once before in the office hours today. But when you take this and you transform it into spherical, remember z is rho cosine phi and r is rho sine phi. And then we canceled out the rows and we said, where is there a place where cosine is equal to sine? And of course, that's going to be at pi over 4. So at pi over 4, we're 45 degrees. That's when you actually enter in. So yeah, that seems about right. 45 degrees or so off of the positive z-axis. That seems to be how we're entering in. And so phi is equal to pi over 4 is how we enter in to our region. How do we exit? Well, exiting had to do with that purple curve. So again, we're going to go back here. Very similar storyline here. And let's see, we take z is rho cosine phi. R is rho sine phi. This one is divided by root 3 here. Cancel these things out. I'm going to go ahead and move that root 3 to the other side. Root 3 cosine of phi is equal to sine of phi. And so the thing is, I remember there's a place where cosine is 1/2 and sine is root 3 over 2. Right? So if you take the cosine value of 1/2 and you multiply it by root 3, you would get the sine value, the root 3 over 2. And of course, this is going to happen when phi is equal to pi over 3. At phi equals pi over 3, the cosine value is 1/2, and the sine value is root 3 over 2. Also, you can kind of just do it from elimination, right? Because when you look at this, you know you're still in this, less than 90 degrees. You've already done pi over 4. There's only one other value on the unit circle, right? That's bigger than pi over 4, but smaller than pi over 2. It's pi over 3, right? So this is going to be phi equals pi over 3. Oops. So that's what this angle right here would be, pi over 3. So our upper bound here would be pi over 3. This one's actually extremely fast to integrate. Let me show you the speedy way to do this, right? So I'm going to integrate theta, done. I'm going to integrate rho cubed over 3. I need to evaluate that from 0 to 7. In fact, I could go ahead and just plug in my 7. Done. And when I integrate phi, I'm going to get cosine of phi, evaluate that from pi over 4 to pi over 3. 7 cubed. That one I don't know. But you would have a calculator, so you could plug that in to get that out. Cosine of pi over 3 is going to be 1/2. And cosine of pi over 4 is going to be root 2 over 2. So you could even, right, there's some 2's on the denominator. You could cancel out with the 2's in the numerator, and life would be grand, right? Or I guess you could just plug this in to a calculator if you'd like. Any questions on this one here? Everyone's still alive.
Yeah, we're doing good, I hope.
All right. I've now had 2 people ask for 27 number 7 to say a few words about that. We just have a couple minutes left, so we're probably not going to be able to do, the problem in its entirety. But let's at least talk about this. Find the volume of a smaller wedge cut from the sphere of radius 7 by 2 planes that intersect along a diameter at an angle of pi over 6. What would be the best method for evaluating this? Well, it's in the spherical section, so probably spherical, but also it's inside of a sphere, right? It's a wedge from a sphere, and so that's another reason why spherical would be really good for this. If you are going to set it up in spherical, I think putting your wedge, right, because it doesn't really say where the wedge is. It's just cut by this diameter here, and it has an angle of pi over 6. So I'm imagining a couple planes here. And so maybe let's orient this so that one of our planes is like this, and then the other one will be off by pi over 6. So this angle right here is pi over 6. And again, it's just going to be along the diameter here. In fact, we don't even need this back piece. So here's the part of the sphere. This almost looks like a taco or something. And it's cut by a couple of planes. Something like that. So notice with this anyway, yeah, so I would recommend saying that the wedge should start at 0. Again, you have to kind of be specific about what variable you mean. So I'm going to take my wedge to be from theta equals 0 to theta equals pi over 6. So maybe right here is pointing out in the direction of the positive x-axis. And then over here is going to be off by this 30 degrees, or pi over 6. When you have it set up like this, what is your smallest and largest phi value that you would want to include in the volume of this region? Remember, phi starts up looking in the positive z-axis, and then it goes down to the negative z-axis. Is there
So
any part
0
of
to
that?
pi?
0 to pi, yes, exactly. So
Sorry.
there's none of that you would like to exclude, right? Because there's going to be parts that you intersect your region all along this. So good. And then let's see, mine, it says we're cutting from a sphere of radius 7, right? So I don't think maybe it's too much of a stretch to say Rho would like to go from 0 to 7, right? You enter in as soon as you take the tiniest step off the origin, and then this blue curve right here, this is the sphere of radius 7, or Rho equals 7. So again, anytime you want to find a volume, that's going to be the integral of 1. Switch it over into spherical. d rho, d phi, d theta. Rhos go from 0 to 7, phis go from 0 to pi, and thetas go from 0 to pi over 6. And all the hard parts done.
Thank you. For me, it was just the way the question was worded. I was just like confused visually, so then it caused trouble. But like from here, I'm good.
Excellent.
Thank you.
Yeah, I agree that this one, it's sometimes very hard to put into words exactly how to describe some region. So
Yeah, I was thinking of the planes like intersecting it differently, so then I was just like yeah. So, but yeah, that makes sense what you did.
awesome. All right. Well, yeah. So this was homework 27, question number 7. So it's the spherical integration bit, the last one that's right technically covered by the exam. Right, homework 27 is what it goes up through, and this was the last question. All right, that's where I'm going to call it for today, guys. Hopefully, I see you on Thursday. Bye and take care.